this is a Verist Engineering webinar called Thermoforming, Materials Characterization, Material Modeling, and Simulation for Better Process Outcomes. I'm Sean Teller. You can see my email there over on the left, and the other host that you can see with the Verist logo behind him is Scott Grindy. And we're excited to talk to you today about this topic. So a bit about Verist Engineering, a little bit by the numbers. We've been around since 2006, so we're hitting our 20 years since we've been consulting this year. We're based outside of Boston in a town called Needham, Massachusetts. And with our facility, we have a 3,000 square foot mechanical test lab. We're currently at 12 technical staff, though we have 3 people joining this fall. We're heavily skewed towards PhDs. And we do work in multiple areas. Today, we're going to be talking about, the 3, maybe in the 12 o'clock to maybe 1 o'clock, nonlinear solid mechanics, material testing and modeling, and materials engineering. But we also do work in product testing, failure analysis, electrochemistry, electromagnetics, multiphysics, heat transfer, and fluid mechanics. We like to say that we're a mechanical test lab built for simulation engineers. We built our in-house mechanical test lab after years of using third-party labs to do the testing and not being happy with the quality or control we got by going to those third-party labs. So as simulation engineers, we developed our lab around that. That means that we don't necessarily always test to a particular ASTM or ISO standards, but we use them to provide guidance to the tests that we're running. And we target and design our test plan to answer questions specifically related to the simulations and the materials that you're interested in. That means we test in multiple rates, multiple temperatures. We'll do multiple loading modes, all sorts of things like that. And oftentimes we might, in the middle of a test plan, we might pause and talk to you, our client, to say, hey, the test data is coming out differently than we anticipated, so we might want to change this, and we'll have a conversation about that. At the end of the day, at the end of the project, we like to deliver simulation engineers the data that they need to advance and validate their models. Scott?
Thanks, Sean. Yeah, so I just want to give a brief overview of the course before we kind of dive in. So kind of on the left, this is probably what you saw when you signed up for the course. This webinar is about thermoforming, kind of the 2 parts of it. So both the kind of materials science aspect and materials characterization aspect, as well as the mechanical characterization required to create FEA models for thermoforming processes. So we're going to do kind of a brief overview of the kind of structure of polymer materials in terms of the different aspects of their structure that can kind of drive the performance related to thermoforming processes. We'll be working on kind of understanding the workflow for designing test programs for thermoforming materials, as well as the actual sort of creating FEA, the steps needed to create an FEA simulation of a thermoforming process. So kind of more specific topics, we kind of divide this in 2 parts. So my background being kind of more in the material science and polymer science side of things. I'll be going first to talk about kind of the material science aspects of polymers. We're going to talk about crystalline and semi-crystalline and fully amorphous polymers, as well as the glass transition temperature and sort of other more kind of temperature dependent properties that are particularly germane to thermoforming applications. We'll talk about 2 kind of material characterization techniques, DMA or dynamic mechanical analysis, as well as differential scanning calorimetry or DSC. And then we'll switch over to Sean, and Sean will talk a little bit more about kind of the more broadly about the thermomechanical characterization, material model calibration, and FEA of thermoforming processes. So to kind of, as I'm sure probably everyone here is aware, but blow molding and thermoforming are 2 very closely related methods in terms of kind of intrinsic mechanical, thermomechanical underpinnings that are used pretty widely across many industries, where you take a piece of essentially thermoplastic material, heat it up and stretch it, whether that's using compressed air or vacuum or a physical tool to make a relatively complex shape. But the kind of the key driver in thermoforming applications is that the cost of designing and fabricating a new tool is quite intensive and very so kind of sensitive to mistakes. So there are only you kind of get locked in on a tool design. And if you find out later that something needs to be changed in the tool, that can be quite costly. And so the idea is that if we can use FE models with advanced material models to simulate the thermoforming process before we actually cut the tool, we can reduce the number of tools essentially that need to be made. You can get it right even perhaps on the first try, which really accelerates the sort of development process, taking a new product from a sketch on paper or a CAD model into something that can actually be formed into a real product. And these processes, these thermoforming processes, and we'll be using just thermoforming essentially as a catch-all for all these sorts of different aspects or different ways of forming thermoplastic polymers. I find it very interesting just personally, because what we're doing is we're heating the material up until it's soft, but not a totally kind of liquid material. So it's different than sort of melt processing that you can do in other thermoplastics. And so you have this sort of mostly liquid but semi-solid material. And then the key kind of point behind that is that if we understand the polymer phase transitions that kind of control the thermomechanical properties of these materials, we kind of need to understand those to understand the different process conditions and variables and things like that that affect the thermoforming process. So I'm going to start by talking about crystallinity in polymers, because I kind of like this sort of diagram that you can see over here on the right hand of your slide, which I like to call the spaghetti structure of polymers. It's something that's generally a good mental model for what polymers look like, is that every polymer chain is this extremely long molecule, generally linear, but not always. But it's useful, I think, to think of them as this sort of spaghetti strands that are kind of all mixed together, all jumbled around. There's not a lot of sort of local order to the polymer chains, sort of in contrast to other engineering materials like metals, where there's a very specific crystal structure. The atoms are in kind of very specific repeating spots that give rise to the interesting properties of metals and things like that. But polymers are different because there are some polymers that have no regions where there's any sort of local order in the polymer chains at all, sort of fully amorphous polymers. But some polymers have some domains, which you can see here kind of highlighted in blue, where the polymer chains like to stack in a sort of specific local order that's called a crystalline domain. And so the crystalline domains in polymers that have them tend to impart things like higher strength and higher creep resistance, things like that. Whereas those aren't present in those fully amorphous polymers. But the key distinction is that all polymers contain amorphous regions, but only some polymers contain crystalline domains. So that's why we call them semi-crystalline polymers, because they have both amorphous and crystalline domains. That degree of crystallinity can range from only a few kind of percent of the material up to pushing 70, 80, 90 even percent of the material, the polymer being in crystalline domains. Most kind of engineering thermoplastics are a bit lower than that. But common examples include polyethylene, polypropylene, and nylon, some of which are kind of commonly used in thermoforming applications. And just kind of as a note, the actual degree of crystallinity can vary strongly, even within sort of different grades of, let's say, polyethylene. Depends a lot on the polymer characteristics, like the molecular weight of the polymer chains, if there are certain additive chemicals added that kind of can either promote or hinder crystalline formation, as well as things like strain and temperature history. So you can, by stretching polymers, you can actually have strain-induced crystallization, just for example. So this is not a case where you can say say to me like, okay, I have this polypropylene, like how semi-crystalline is it? I can't answer that question for you necessarily. To a reasonable degree of certainty. It's kind of the thing where we have to measure each kind of individual polymer and sometimes each individual product. And so, more relevant for our discussion today about thermoforming materials is that, both fully amorphous and semi-crystalline materials are commonly used in sort of different thermoforming applications. So things like ABS and polystyrene, which are very commonly thermoformed, those are fully amorphous polymers. There's no crystallinity there. So it's, not part of the intrinsic structure of the material. On the other hand, polyethylene, or HDPE, which is extremely commonly thermoformed, blow molded, is essentially always semi-crystalline. So you do have to consider the interplay between the amorphous and crystalline domains when thinking about kind of the structure of the material and how you analyze that material. But I think maybe most interesting is PET, which is obviously like very commonly thermoformed or blow molded. Soda bottles being the kind of thing that we interact with on a day-to-day basis. But of course, PET packaging in things like medical devices and the image that you can see here, obviously prized for its clarity and in addition to its interesting mechanical properties, because PET is kind of intrinsically a crystalline material, but you can process it in such a way to kind of prevent those crystalline domains from forming. And so kind of understanding the potential for forming those crystalline domains, which actually, if you do form them, will cause the material to become opaque instead of clear, could be a kind of a critical failure mode of your packaging, because if you can't see what's inside, the consumer's not going to like it. That's a real failure mode that needs to be considered. And so, we're going to talk a little bit about the glass transition here. This is something I think kind of anyone who engineers a product with plastics or polymers needs to kind of understand. So I talk about this in lots and lots of the different webinars that we give here at various, at least the ones that I give, because I think it's maybe one of the more important concepts in kind of polymer science. But you can think of it like somewhat equivalent to kind of melting, which is where you have at lower temperatures, and this is a graph of kind of the modulus of a material versus temperature. At lower temperatures, you have a very sort of rigid material, and once you pass through that glass transition temperature, the modulus here drops down by kind of about 2 orders of magnitude until it's becomes what we would call rubbery. The difference between melting and a glass transition is if you're trying to impress your friends at parties, you call it a second order phase transition instead of a first order phase transition, which melting is. But it affects how we actually measure kind of where this temperature is. And the other kind of important thing about the glass transition temperature is that it tends to be kind of a range of temperatures. You can see that the drop in modulus for this particular material starts dropping at about 60 degrees C and finishes dropping at about 100 degrees C. So that means that kind of anywhere within this range, you have a pretty strong sort of sensitivity to the temperature. And so as we step through this is kind of the way I in cartoon form, the thermomechanical behavior of polymers reduced to kind of sort of one cartoon, which is as we think about the material stiffness versus temperature, at very low temperatures, for semi-crystalline polymers, we have glassy amorphous regions because we're below the glass transition temperatures. Those amorphous domains are rigid. As we go through TG, those amorphous domains become rigid, but we have those crystalline domains still. So we still have some sort of reasonably high modulus. As we go through the melting temperature, those crystalline domains melt, and we have a very, very soft material, viscous fluid in some cases. In contrast, for amorphous polymers, this sort of diagram looks a little bit simpler because there's really only one transition. As we go through TG, we go from glassy amorphous domains to rubbery amorphous domains. So we're going from a sort of harder material into this softer, kind of more rubbery material. And tools that you can use to measure essentially the thermal properties of these kind of polymers that are relevant to thermoforming. The one I like to talk about first and like to talk about the most is dynamic mechanical analysis, or DMA. This is the measurement tool that even if you're not looking at a thermoforming polymer, I kind of strongly recommend kind of folks get a DMA temperature sweep done on essentially any plastic that you're using in your device, because it reveals lots of useful information that we're going to talk about in a little bit more detail. But kind of fundamentally, the DMA is a mechanical test. We have a sample, it's in black here, that's in a sort of tension grip. There are other grips that you can use. And then this hood here, which is sort of an oven, comes down. It's a forced convection oven. And what we're going to talk about today is a way of measuring what's called the dynamic modulus, or the complex modulus of the material, storage modulus, and the loss modulus as a function of frequency and temperature. And we're not gonna talk too much in detail about kind of the other ways we can use a DMA. I think today we're mostly going to talk about what's called a temperature sweep, which is a type of test where you're measuring the storage modulus, which is essentially the elastic modulus of the material, and the loss modulus, or E double prime, as a function of temperature. And so this particular example is for nylon 6, which is a semi-crystalline material. And so as we go from minus 100 C up to just above 200 C, I've kind of pointed out two spots that I think are most interesting to the material. So one labeled number 1 and one labeled number 2, both where the storage modulus, essentially the elastic modulus, decreases sharply. And so as we go through this, you can see at point number 1, we have the strong decrease in the storage modulus and this local maximum in the loss modulus. And that's kind of characteristic of the glass transition of materials. And so most nylons have glass transition temperatures about in this kind of 50 to 60 C range, give or take. And so you can see actually this happen kind of over the course of this as we heat up the nylon. At point number 2, this is the melting point for that nylon. So as I said, nylon is semi-crystalline. And so this is where we're actually measuring sort of the onset of melting for these materials. And so we can use the DMA to not just measure these sort of characteristic temperatures, the melting point and the glass transition temperature, but just as kind of an engineering exercise, it's very useful to think about how the stiffness of your material changes with temperature, kind of help assess, what are the risks of various failure modes or excess deformations across different temperatures, versus in sort of shipping versus storage and things like that. So, if you're using a polymer or plastic in your product, I couldn't recommend it any more strongly, just getting this data. It is just small strains, does not account for kind of many other things that your products will see, but it's a lot of information from one single test. And so this is kind of my strongest recommendation for using the DMA. I'm going to transition a little bit to talk a little bit more about a different technique that we can use to kind of measure the structure of thermoplastics, things like the glass transition temperature, the melting point, as well as the crystallinity, essentially the degree of the specific degree percentage of the material that is crystalline, and it's differential scanning calorimetry. Spend a little bit more time on this because I find it to be more of a counterintuitive or sort of like less straightforward technique to grasp, because it's fundamentally it's a thermal analysis technique. It's calorimetry. What we're doing is we have essentially two crucibles, one that has your sample in it and one that's just empty. And the DSC, the tool itself, is kind of programmed to heat both of these crucibles at the exact same rate. So typical rates are kind of between 1 and 20 degrees Celsius per minute. Just as a kind of a baseline to compare to. There are other methods to use extremely high heating and cooling rates, but that's kind of the standard for these. And one thing to note is that we're usually using only about 5 to 10 milligrams of sample. So one of the real advantages of DSC is that you do not need very much material. You can take an extract from a product that comes off of a tool, comes out of the field, without having to worry about creating a nice sort of mechanical test sample like you do with the DMA. But what we're actually measuring is the amount of energy required to maintain that heating rate in the sample relative to the reference. So if you take basically the difference between the heat flow for the sample and the reference, it is the actual output of the DSC. And so using that curve, that sort of heat flow versus temperature curve, which is the specific result of the DSC, we can actually measure TG, we can measure the melting point and the percent crystallinity. We can look at something called cold crystallization, which is especially relevant for PET. And so we're going to talk about that in a little bit more detail. You can also measure things that are perhaps not quite relevant to thermoforming applications, but you can measure the material's heat capacity, and you can actually measure kind of chemical reactions like curing of thermosets and things like that. So those are kind of more advanced methods that you can use a DSC for. To look at some actual results. So this is what the actual results of a DSC trace will look like. This is a heating curve for a polystyrene sample, and so polystyrene is a fully amorphous polymer. So what we see is a glass transition right before 100 C. So the TG of polystyrene is typically around 95 Celsius, something in that range. And this is what these really look like. So this is a fairly weak signal. It's pretty common for a lot of amorphous materials when you're looking at trying to measure the glass transition temperature with DSC. So this is the kind of technique where it does take a little bit more experience, something of a trained eye to actually pick out what's TG and what's just noise. But this is how you measure that for a fully amorphous material. Kind of in contrast, and this is where I want to talk about PET a little bit more, there's a lot more to be seen on this curve. So you can see the TG is actually a bit of a stronger signal for this material, but then there are two peaks. There's kind of a positive peak here, which I've labeled as crystallization, and a negative peak here that is I'm calling melting. That I've labeled as melting. So what's happening here is that to take one step back, so that clear PET that is most commonly used for thermoforming applications because it's clear, you can see through it, it makes a nice packaging material, is processed so that it's fully amorphous. So even though PET kind of intrinsically wants to form crystalline domains, if you quench it, if you cool it really fast from a melt processing step, you can prevent the nucleation and growth of those crystalline domains and maintain that clarity. So what happens is we heat the PET up, it goes through TG, it's much, much softer. And as we add essentially enough thermal energy to the system, the polymer chains are able to move around much faster. And when they're able to move around much faster, they can find the orientation where they form those crystalline domains. And that you measure that as, in this case, an exotherm in the DSC trace. That actually releases heat. So basically, as we heat this up, we are allowing the kinetics of that phase transformation to be fast enough so that it happens kind of on a relevant experimental timescale. Now, as we keep heating the PET up, we reach the melting point, and all of those crystalline domains are going to melt. And so if you take the area under these curves, then you can actually use that to calculate the kind of degree of crystallinity in your PET material. And so, which is, potentially most relevant to this audience here today, who's interested in kind of thermoforming applications, the kind of thermoforming range for PET means that we need to heat it above its glass transition temperature, but we don't want any of this cold crystallization to occur. Because as soon as we start getting cold crystallization, we get something that looks like this, which is, it's not clear anymore. It's not a nice packaging material that we like. And so just to kind of dig into that a little bit further, this is a DMA temperature sweep on sort of thermoforming grade PET. And you see something similar to what we saw in the DSC trace, where kind of at cold, low temperatures, we have a very high modulus. It drops as we go through TG. And then once we hit, about 130 degrees or something like that, this material actually stiffens because we were forming those crystalline domains. And as we heat it up even more and more, it'll start to melt. Our modulus will start to drop off. So you can use a DMA to measure these types of things as well as a DSC. But in terms of kind of more advanced applications of this technique like this, you can actually use different heating rates and you get different traces. Basically, the glass transition temperature will shift up at higher heating rates, as well as the sort of nucleation and growth kinetics of the PET will kind of shift to higher temperatures because it's fundamentally both kinetic processes. And so you can use data like this to calibrate a kinetic model for the kind of time temperature transformation of the PET from its amorphous to its crystalline state. Essentially, we're calibrating a model for the crystal nucleation and growth of the PET kind of as a function of both time and temperature. And so you can use a diagram like this one on the right to help understand where the risks might be in your various processing conditions. So you spend a certain amount of time at 120 degrees C. This is in log time space, right? This is right about a few seconds at 120 degrees C, then you're at risk of getting about 0.1% crystallinity. And so, kind of using a diagram like this can help you assess, different basically temperature histories for your thermoforming process and identify things about, potential risks of crystallization. And so with that, I think I'll hand things over to Sean, who's going to talk a little bit more about the FEA modeling side of things.
Thank you very much, Scott. So I'm going to go through a case study here on how we would do testing and modeling of materials if you're going to simulate a thermoforming type process. And I'm going to use an example to talk about blow molding. So in this case, we're actually looking at a PET material, which is a thermoplastic material often used in kind of plastic water bottles or soda bottles. And this is what we would call, a custom design test plan to understand the material response. And then use that to inform a finite element model. So here I'm showing results from 2 tests where we're looking at the temperature dependence of this material, and we've done this at 90 and 100 C, 90 C and 100 C. And we've done this specifically at those temperatures because we've done some of the tests that Scott has been talking about, some DMA, some DSC, to understand how the material changes at those temperatures. And this is in the processing range that we're interested in for this material. And if you look at the one on the right there we're plotting engineering stress versus time. And we're doing a cyclic test where we load up to a certain strain level, and then we hold that strain for 30 seconds. And then you see the stress relaxation. And then we usually do a little bit of unloading, and then we go up to the next strain level. And we repeat that. In this case, we did that for 4 levels, and we went to failure. So both of these materials failed, and we got and that's how we got those curves. So that loading and unloading we find is very important to help understand the time-dependent behavior of the material, because we measure that stress relaxation, and we measure that amount of stress relaxation at multiple strain or multiple stress levels to understand how linear or non-linear it is. One thing to call out here is that there's a large difference in the material response between 90 C and 100 C, right? So at 90 C, we peak at about 2.5 MPa, whereas at 100 C, we're at just, we'll say 0.9 MPa. So that's a 2.5x difference between that. So there's a large stiffness difference. And the other thing that I like to point out is by doing this one test, we've gotten stress relaxation data at multiple levels. We've gotten unloading at multiple levels. And that's important because as we do this type of thermoforming, we don't have a uniform deformation in the field. In the part that we're making, we have variable deformation where some areas have been stretched a lot and thin out a lot, and other areas have not been stretched. So understanding how those are going to relax is going to be important. Similarly, a little bit of slowness here. There we go. Similarly, we can see what happens as we change the strain rate here of this material. So here we've done tests at 2 different strain rates, and this one I believe is at 90 C. And here you can see the time effect or the strain rate dependence that we see in this material. So the blue curve we did at 0.1 strain per second, so we get to 10% strain in 1 second. So it's a moderately fast test. You can see there that's what we had previously. That peaks at about 2.5 MPa. And then the green curve is what happens if we go an order of magnitude slower. So it takes 10 seconds to get to 10% strain. So it's taking 10 times as long, and you can see there that we're softer. We peak somewhere, we'll say at about 1.5 MPa. So that's a pretty large difference between those two. So we see this temperature dependence, and at the temperature that we're interested at, because we're near one of those transition temperatures that Scott was talking about, we're getting a very different material response when we look at the temperature. Similarly, although we haven't really discussed it today, time and temperature are related in polymers. So we also see a lot of rate dependence at this rate, where we might not expect to see this much rate dependence, a 50 to 60% increase in the peak stress with an order of magnitude change in the strain rate. We might not expect to see that unless we're at one of these transition temperatures that Scott was just talking about. So I'm not sure how that video is coming through for you. It's a little jumpy for me, but you can see there that there's a video where we've done some advanced strain measurement using a method called digital image correlation, or DIC. So what we do in this test is we apply a speckle pattern. So there you can see that we've taken the clear material, we put a base coating of silver ink on there, and then we put a bunch of black dots on there. So that random stochastic pattern is just there for us to track it. And we take hundreds to thousands of images during the test, and then we post-process it in a very similar way that finite elements are post-processed. And then we can measure the strain in a non-contact way. And this can be a great tool because the strain measurement does not impact the strain that we're measuring. It doesn't add any force to the system. We can do it at high temperatures, low temperature, room temperature, very fast rates, very slow rates. And then it can also let us look and see if there's any sort of non-uniformity in the test. The PETG in this case shows a very uniform deformation where we don't see what we call necking, but we can see that in this test, and you can use that to analyze data in different ways. So we do this for the majority of the tests we do here at Varus Engineering. We use commercial software to do this, and it helps us get accurate data at all sorts of conditions using the same method. And so we find it to be a very powerful tool for selecting material models and getting data on polymers. So I talked a little bit about the test data that we have. So what I did in the next step here, and if you remember back to a slide at the beginning, we talked about that process where we do testing, then material modeling, then finite element simulation. This is the material model we calibrated to this test data. This is called the Bergstrom-Boyce model. One reason I like it is that it's an advanced model that captures elastomer-like response very well. It's I call it a nonlinear viscoplastic model. Some people call it a nonlinear viscoelastic model. We could have debates about that all day. I'd be happy to do that with you over a coffee or a beer. But the other reason I like it is that it's available in all all modern finite element code. So you can find a version of this in Abacus and ANSYS and Ellistina and COMSOL and Radios and in Mark. And I'm sure there are others I'm leaving off there, but it's been around for a while and it's been implemented, and because it is such a powerful model. So when we calibrate it, we have 7 parameters that we need, and I've shown the structure of the model there over at the left, and I've color-coded it to help us understand what's going on here. So in this model, we have 2 parallel springs shown by the green and the blue squiggles, and we're going to call each one of those legs a network A and a network B. The stress in network A is given by that blue equation, which if you have seen this before, that's the Arruda-Boyce or 8-chain hyperelastic model. So that's a non-linear, completely elastic model. And we can see that there are 3 parameters there. There's a bulk modulus kappa, there's a shear modulus mu, and then there's a lambda L, which is a locking chain stretch. So that gives us an elastic response. The green data there, or the green equation there, is the stress in network B, which is the stress in that hyperelastic spring. It's the same thing as A, but we put a parameter S in front of that shear modulus mu, and that gives us a way to change the stiffness, relative stiffness between these 2 networks. The third one is the shear flow rate of that dash pot given there in red. So this is sometimes called a Bergstrom flow element. And we've got another couple parameters there. 1, 2, 3. Depending on how you count. 1, 2, 3, 4, 5, 6, 7. Which is a little much because some of those we actually end up fixing. Tau hat cut is usually fixed. Gamma dot 0 I fix as well. So really we're looking at tau B, C, the Greek letter C, and M to help us understand that. So that'll give us that. And the power of that is that it gives us a time-dependent response that is non-linear. We have all these exponents here. That is non-linear and can capture the complex behavior of these materials. So what does that mean in practice? So here's a material model I calibrated to that data. So the solid lines are the tests. The dashed lines are material model predictions. And you can see there we've got a very good prediction between those 2. We're capturing the stress strain response very well. We're capturing the unloading well. We could do a little bit better in capturing the hysteresis. The hysteresis is when we do that unloading, say on that red curve at about 100% strain. When we unload, we don't exactly follow the loading the unloading path back up. That's some hysteresis. We're not quite capturing that, but overall, I'm very happy with this model. We're capturing that large strain response of this material, the rate-dependent response, and we're doing it accurately here. This is a well-calibrated model. But what do, before we get into that, the other thing we want to talk about is a little bit more of that time dependence, right? So if we look at the stress versus time for that cyclic test that we did, we can see here that we're capturing the stress relaxation very well. And it's not perfect. You can see that the first two stress relaxations, up at about 0.5 and maybe 0.75 MPa, we capture very well. Getting the shape well, we're at the peak and the minimum very well. But as the other two, we go further and further up, you see where the shape is a little bit different. And this is just something the model isn't capturing. But overall, we're capturing that trend and that response very well. So we're going to get the rate dependence where we see a material that's stiffer as we pull it faster and faster. We're going to get the stress relaxation effects. That means we're also going to get things like creep. So we're capturing this model response well. But what is this model? How does this model behave? I showed you kind of all those parameters. I showed you that schematic, but what does each one mean? So I've taken just one of our curves there, that green curve at the lower rate. That's a tension test, and I've tried to show kind of what happens in each one of them. So in that first, say 20% strain, where we've got a moderately straight line, at this point, the dash pot is not activated. To really get, and by activated, I mean, we're not getting a lot of strain or displacement in that dash pot. So really, we're just have a model that has the stiffness of network A and network B. And if you work with these models long enough, you'll see that at that small strain range up to 10, 15%, you're not going to see a difference in any of the rates, and everything's going to be right on top of each other. But then we get a shift in the curve at what's happening at, say, 25 to 50% strain, where it's much softer. That portion there that I've circled with in blue is when the dash pot has yielded. That's why I like to call it a viscoplastic response. We're getting a lot of deformation there. And what that means is that we really just have the stiffness in network A. As we pull on this and we pull on this, all our forces going into network A. We have a very low force response due to that dash pot. So we get a much softer response. And that's why we get that kind of response. And as we start to talk about cyclic behavior, I've taken that red curve there, and again, I'm trying to show what happens. So as we load this up, remember at the beginning, we're loading up, we've got the stiffness of network A and network B, and then we do a stress relaxation and we hold it. And as we drop there, what's happening is we're going to an equilibrium condition where the dash pot is allowed to kind of have some deformation over a very long time period, and then we're only going to have the stiffness of the A network. And so that's why we see that drop. And then we reload and we see the same drop here again at 25%. But as each one of those reloadings that we have, we're getting the stiffness of network A and network B again, where you can see that the slope here matches the slope here pretty well. So that's a little bit of a primer on the Bergstrom-Boyce model, which you can use in all major finite element codes. But now I want to talk about the simulation that we're running, and how we're going to use this model to then really help understand thermoforming or blow molding to help you design your process well. So here I'm showing the simulation that we're running. So we're doing a blow molding process. So that one we start with a blank. And then we apply some pressure internally, and this thing blows up, gets larger, and then typically you ramp that pressure up, and then you wait a little bit of time, and the material creeps into its final form, and this kind of looks like a bottle that you might expect there. So we're going to ramp that up quickly over a tenth of a second, where we're ramping that pressure up, and then we creep to that final shape over a brief period of time on the order of seconds to get that final shape that we need. So here's some simulations, animations from the simulations where we're going to let this run a couple times. So over on the left, you can see the stress in the bottle. Right, we get a lot of stress down at the bottom because we've deformed it significantly. Over on the right, you can see the displacement where we're going for 62 total millimeters of displacement. It's a very large displacement model going on there. And you can see that the simulation actually has two components. There's the blank in the bottle that we have. And then there's actually a mold that this is being compressed to, right? That's what gives it that final shape. So this is the simulation that I ran with that material model that we talked about based on the test data for the PET. And as I kind of foreshadowed at the beginning, we did this testing at 2 different temperatures. So what we've done here is we've tried to look at the difference in the material response at the same time of loading for those 2 different temperatures. So if we run this at, say, 100 C at the same time, you can see that we've almost filled the bottle. So that one on the left shows that we're almost completely full there. We can see the stress as well as the displacement, right? We're getting higher stresses, we're getting more displacement. We almost filled the bottle, we're going to get there. But if we look at the 90 C one, at that same pressure and at that same time, you can see that we've only expanded the blank a little bit. And, this is intuitive to us. We know that these materials are much stiffer as they're getting colder and colder, or closer and closer to room temperature. But look at how much of a difference that is. That's the difference between, on the left, your process working, and on the right, your process is not going to work, and you're not going to get a bottle at the end of the day. You might say to me, Sean, well, what happens if we go to even higher and higher temperatures? Right? Isn't that going to get better? Well, as Scott talked about earlier, where we have these crystallization effects, that's not always true. So I'm bringing up the monotonic data we had for 90 and 100 C, right? And you can see there that we're getting a very different response based on that temperature between there. But if you look closely, you're going to see that this is a little bit different than you would expect. Is that labeled backwards? Excuse me. There we go. What we're going to see is that as we go to higher temperatures, we might not always get the trend that we expect. So here at 90 C, we have a stiffer material. 100 C, it drops pretty significantly, a factor of 2 or 3. And then as we go, you'd expect the same thing to happen at 110 C. But this red curve is what happens when we do that same PET material, but do it at 110 C. Now that's a much stiffer response, right? Even at small strain, where maybe 2x the stiffness or the strength of the other materials. But if we go to those much higher ones, there you can see there we're at these huge stress levels where we're 4, 5, 6 times as stiff. That's because the PET is showing cold crystallization, so we're getting a change in structure due to that heat. And as that happens, we're getting a stronger, stiffer, and ultimately more brittle material, and that's going to make our simulation process much more difficult. I think that is about it. So we've got about 15 minutes left for classes. Here we're doing a little bit of an advertisement for our upcoming webinars and seminars. So in 2 weeks, we have one from our colleague Joe Barakat, who's doing one for CFD modeling. And then there was, we got adhesive testing and material model calibration on September 10th by our colleague Mark Oliver. And then I have a paid online class in September on material testing and modeling, September 15th through 18th. So that's 2 hours a day for 4 days, where I'll talk to you all about polymer testing, modeling, and how you can do those types of things. So there's some QR codes up there. Please feel free to use those to look at what's available. And we'll be putting some more free webinars in the coming months. We do about 2 a month. So if you'd like to, you can also be added to our email distribution list, where you'll get notifications of that, or follow us, one of us on LinkedIn, and you'll usually see that. I believe that is it. So we're just going to open this up to any questions or comments you might have. And please feel free to reach out if you would like to talk at all about any sort of problem you're having or issue you're thinking about for polymer testing, modeling, characterization, failure analysis, anything like that.
Yeah, Sean, I'll start sort of feed you some questions. So it looks like they're mostly for you. So first question, is it possible to use 2D shell elements and still extract a meaningful final thickness distribution?
Oh, yes, but I would think, and I always have to look, I would have to look in each one, but I would use thick shells in that instance instead of normal shells, where they're formulated, in my experience, typically gives you a slightly better thickness prediction from that. But yes, you can use that. You can use shells, but I would use whatever your finite element code thick shell implementation is.
Okay. Next question: does the model encompass both slow creep and rapid drop impact?
Good question. So that model can. In this case, we didn't have like drop impact data for that material, because the other thing to think about, that we can have a model that does that. The other thing to think about there is we're probably not interested in drop and impact at 100C or 90C. That's the processing temperature, right? So we did that testing to do the thermoforming at the elevated temperature. And then if we wanted to do impact testing or impact modeling or drop modeling of the bottle after it has been formed and a consumer is carrying this bottle around, then we'd want that data at room temperature. So this model can definitely capture that. But in this case, it wouldn't have made sense to me to do that at 90 or 100C, but I do that at 23C and use that both a temperature dependent model as well as a rate dependent model.
Yeah, next question. Is there a comparison of the resulting thickness distribution and resulting residual stress distribution between simulation with the fitted material properties versus experiment?
In this case, no, because this is an example I had to make up without any sort of client data. So I fortunately don't have the ability to blow mold those bottles. We've done similar projects in the past where we have, because that is a key way to validate the models and is usually very critical to make sure that kind of, if you're talking about those drop simulations afterwards or performance afterwards, it's very critical to make sure that those match, because a lot of times those thinned areas are where you would expect to see failures. So I think that is something that you can and should do, but we don't have it in this particular case.
Okay. Next question: what tests and how many variants, temperature, rates, etc., are typically needed to fully fit a BB model, like the one you showed?
Good question. Rates, I like to test it every decade or two of strain rate, getting at least 2 strain rates. So there I'm going to look at what the strain rate of interest is for your particular application and material. So, if you need to go from 1 times 10 to the minus 3 times 1 to the 3, that's going to be 3 to 4 strain rates. But if you're only at, moderate speeds, you might only need 2 or 3. Temperatures, part of it depends on doing an initial test like Scott talked about, like a DMA, to look at the temperature dependence, and then we narrow down the range there. If you have a very tightly controlled process and you're only going to be between 90 and 100C, that's probably all you need. But if you're using this material in multiple processes and you might go between 80 and 105, we might want to do 3 temperatures in that range. So those are kind of some rules of thumb. But I know that's not a hard answer to you, because part of it depends on your application. We talked about temperatures. We talked about rates. Was there anything else I missed there, Scott? Because I seem to be getting these questions significantly later than you for some reason. Because I just saw the first one. I do see one here. Bergstrom Boyce only an isotropic material model. What is a good anisotropic material model to use for thermoforming? Yes, the Bergstrom Boyce is only anisotropic. What is a good...
Sorry, only isotropic.
It's only isotropic. Thank you, Scott. What is a good anisotropic material model to use for thermoforming? Built into a finite element code? You're going to have to make some painful trade-offs, I think. If you're an abacus, you could do an anisotropic hyperelastic model with linear viscoelasticity. You could probably do a decent job with that, but it's not going to be perfect, and you're not going to get any sort of anisotropic yielding. It's all going to be anisotropic elasticity. Elastina would be something similar to abacus. ANSYS would be something similar to those two. So those are the 3 I can think of right now. Built-in models, there's not a lot of anisotropic rate and temperature dependent polymer models. So you are a little limited there. The PolyUMod library from ANSYS /polymer FEM does have some that would work well. So there I'd use the TNV or 3-network viscoplastic model. But that is an additional licensing cost as well as computational cost to run those simulations.
Actually, I'll piggyback on one of these questions. Can I ask you another question, which is sort of, when would you recommend using a material model that has a sort of intrinsic temperature dependence, or versus a sort of single temperature material model, both in terms of the model calibration, the testing involved, as well as the specific model choices?
Good question. So Scott's talking about a feature in most finite element codes, Abacus and ANSYS, the two that come to mind, where I can define a material model at 90 C, and then I can define the same material model at 100 C and give it that temperature. And then what Abacus and ANSYS will do is linearly interpolate that material response in between those temperatures if your simulation is in between those temperatures. That can be a good way to get temperature dependence, and is oftentimes how we have to do it. The advantage of it is that you can basically get any temperature dependence you want theoretically, because you can play with those parameters as much as you want. The downside is that you'd have to be careful with those parameters, because you're doing linear interpolation over for a non-linear response. So trying to be careful in how you choose those parameters and restricting them when you optimize them can be critical to make sure that you get a simulation that behaves well and converges. So that's kind of that's me standing on my soapbox about that. What that means, though, is that that's usually how I go, because there are not a lot of material models that have the built-in temperature dependence. Or if they do, the form ends up not fitting what I need. For example, there's a 3-network model that's available in ANSYS and LS-DYNA and COMSOL and ADINA. And it has a temperature dependence, but it's a very limited form. The modulus has a linear function, and the yield stress has a power law function. And part of those two are related. So it can be great, but it can also not be great. You're not going to get that transition like through any of the transitions that Scott was talking about. So it's always going to depend on what your temperature range is, how your material response changes. But usually, we try both methods and see which one works best.
Okay, I think, here's another. Yeah, if you have a thin film for thermoforming that is multi-layer, how would you characterize that material? Would you want to do each layer individually? What would you do about that, Sean?
That's a good question. I would probably do a little bit of both. I would probably do some, because I've done this. I have done this before, actually, where I would start with the 2 component layers, do some testing independently there, and then do a validation on the layered structure. It does make your simulation a little more computationally expensive, because you're going to have to use, either continuum elements or some shells that have tied nodes together to make sure they track. But that's how I would do it. Is I would start with each individual layer, validate both a uniaxial tension in plane test of the multi-layer structure, as well as some sort of bending or punch or something like that to validate the material model, and then simulate it with the 2 layers and the 2 different constitutive models. I think you'd lose too much by just trying to do it as a monolithic homogeneous material, and so I think that's going to give you the better response. I do see, how do you decide between running thermoforming using finite element solid solvers or flow solvers like ANSYS Polyflow? For me, that's easy. I don't use Polyflow, so I do it in finite element analysis. That's a little bit of a glib answer. Part of it depends on kind of what you want to do with it. If all you're going to do is the process simulation, Polyflow might be a little bit better. I'm not as familiar with it, so it's hard for me to say. I'm not sure how complex their material models get. But if you want to thermoform it, then take that thickness and do like a drop test like someone else is bringing up, then I think you want to use solid mechanics. depending on your geometry, running these in an explicit solver with shell elements is not that computationally expensive. So I think it's worth it to not have the headache of trying to go between two different codes and transfer results and all that kind of thing.
Next question, is it possible to add cooling analyses on top of something like this to look at full cycle time and further downstream mechanical analyses like residual stress?
Yes, you can. It always gets tricky to get the data you need to understand how not just how the material cools, but how it solidifies. But Scott and I have worked on projects like that where we use a combination of the approaches that you see today and validate it. So that is possible to simulate, heat it up, press it, cool it down, drop it with something. And depending on your industry, your timelines, your cost. The other thing that we worked with clients before on is kind of, you don't worry, you might be able to get a lot done with not worrying about the exact cooling. So you thermoform it, and then you kind of export the results there and say, this is my deformed shape, and then you drop it. And that can work really well as well, and get you, it's one of those things that might get you 80% or 90% of the way there. But if you're currently doing nothing, that is a huge improvement over cut a tool for $100,000 and drop some things, and I hope you don't have to cut another tool.
So I think that's it for all the questions, unless I'm missing one. Hopefully not.
I think so too.
So thank you everyone for joining us today. It's been really fun. Lots and lots of great questions, which we love to see.